So anyway, yeah, thanks Ben and Chong for organizing this session on architecture design. And so yeah, I don't think Ben is a research scientist, works at the Johns Hopkins University, and Chong Yu is currently a postdoc at the UC Berkeley in my group. Thanks for organizing this. Yeah, it's all yours. Thanks.
Okay, great. Yeah, all right. So yeah, so thank you everyone for joining this sort of last session of the CDTI workshop, and also to those of you logging in on YouTube. So the last session here is really going to be about emerging and open sort of questions in principled neural architecture design. Right, so I'm going to sort of start off with a overgeneralization here and say that a lot of neural architecture design sort of to date has been driven arguably by intuition and somewhat empirical trial and error, right? So obviously that's kind of a oversimplification, and a lot of that we're going to hear from today have done work that would sort of refute this statement. But by and large, I think a lot of people would sort of agree that the field as a whole, this is kind of what's happened. And so really the session goals today are really to try to sort of identify key open questions that will enable sort of principled architecture design. And so, what is meant by principled depends a lot on what your goals are, whether you want robust statistical generalization, maybe you want efficient inference, et cetera. And so we'll hear from sort of a variety of expert panelists today who sort of different viewpoints. I think we've sort of invited a very nice panel, so hopefully everyone finds it interesting. And then the second part of the session will really be sort of an open discussion to really talk about potential technical approaches to these open questions. And so just very briefly on schedule, I'm just going to introduce all of the panel up front. Just to sort of, in the interest of time, a little faster transition between speakers, and then we'll hear invited talks from all of the panelists. I'd ask that everyone sort of hold questions until the end, just also in the interest of time, and then at the end we'll have plenty of time for questions and discussions with the panel. All right, so with that, I will begin. Our first panelist will be Qiang Liu. I'm going to apologize in advance if I butcher anyone's names. Everyone has an open invitation to butcher my name as well. But Qiang is an associate professor of computer science at the University of Texas, Austin. He works in many areas of machine learning, statistical learning, and reinforcement learning. He's an action editor at the Journal of Machine Learning Research, and really he's done some very work lately on sort of principled ways to design and learn actually neural architectures directly from data. Next, we'll have a talk from Tesh Schmidt. Tesh is the 2018 Alvarez Postdoctoral Fellow in Computing Sciences at the Lawrence Berkeley National Laboratory. Her interests include building neural networks from first principles for rich data types, such as those found in scientific data sets, and creating new capabilities for chemical and material design. She really comes from more of a physics background, earned her PhD in physics at UC Berkeley in 2018, working with Professor Jeffrey Neaton. In addition to her PhD work, during her PhD time, she also spent a year interning at Google's accelerated science team, where she developed new convolutional neural network modalities called tensor field networks, also known as Euclidean neural networks, that can handle data that comes from 3D data geometries and properties of physical systems. So for those of you that were able to see Max Welling's talk, for example, earlier in the workshop, very much related to ideas like incorporating equivariant and invariant design into neural networks. After that, we'll have Chong Yu. Chong is a postdoc at the University of California, Berkeley. He received his PhD in electrical and computer engineering from Johns Hopkins University in 2018, where he also won the doctoral dissertation award that year from the Mathematical Institute of Data Science at Johns Hopkins. His research includes machine learning, computer vision, optimization, and signal processing, and he's interested in the development of mathematical principles and practical numerical algorithms for analyzing and interpreting modern data sets, particularly those that arise in real world challenges. Next, we'll have a talk from Anima Anand Kumar. Many of you are probably familiar with her work. She is the Bren Professor at Caltech and the Director of Machine Learning Research at NVIDIA. She's won many numerous awards. In addition, she was previously the principal scientist at Amazon Web Services. She's been honored with the Alfred P. Sloan Fellowship, the NSF Career Award, the Young Investigator Award from the Department of Defense, as well as faculty fellowships from many industrial companies such as Microsoft, Google, Facebook, and Adobe. She is part of the World Economic Forum's expert network, and she's passionate about designing principled AI algorithms and applying them in interdisciplinary applications. She's worked in a wide variety of fields in unsupervised artificial intelligence, optimization, and in particular tensor methods, where she's made many seminal contributions, and as well as relating those to and incorporating them in neural networks. And then finally, our last panelist will be Song Han, who is an assistant professor in MIT's Department of Electrical Engineering and Computer Science. He received his PhD degree from Stanford, and his research primarily focuses on deep learning computation. His work has won many awards in low-power computer vision contests and conferences such as CVPR, ICCV, and NeurIPS. He's also received Best Paper Awards at other premier conferences such as ICLR and FPGA. He's won many faculty awards from various industrial companies such as Amazon, Sony, and Facebook. He was named to the 35 Inventors Under 35 by MIT Technology Review for his work on deep compression techniques that allow artificial intelligence algorithms to run on very low-powered mobile devices. He's also received the NSF Career Award. All right, and so with that, I think I will turn it over to our panel now, and I think our speaker will be Qiang Liu.
Okay, thank you very much. The open question that I want to discuss today is how can we design mathematically principled neural architecture learning algorithms that can go beyond black box optimization. Neural architecture optimization is really, I think, obviously an unsolved question in deep learning. It holds a promise to lots of critical areas. Better neural architecture can give us a boost on accuracy far beyond parametric optimization. It enables automatic deep learning. It's a component of automatic deep learning for machine learning. It allows us to design computationally energy efficient architectures for edge devices, right? Also, if we can adaptively grow and shrink our model, then it will provide a very useful tool for transfer learning, multitasking learning, and meta learning, where we are handling lots of different changing tasks and data sets, right? Compared architecture learning to parametric learning, we will see a huge difference. So parametric learning, parameter learning, weights learning has been really kind of solved in the sense that we can apply one single algorithm called gradient descent, variance over a stochastic gradient descent atom or AdaGrad, that can solve the problem very efficiently, right? We know that the gradient information provides a really critical role. If we do gradient-free optimization, for example, we wouldn't be able to train these large-scale neural networks at all. Using gradient information allows us to guide search more efficiently in the high-dimensional space, right? And this is an interesting thing, that this whole area of deep learning is actually rely on a single algorithm that is so simple and elegant that you can teach in undergraduate class, right? And what's more importantly, this whole single algorithm gradient descent is actually supported by a huge, vast literature on optimization theory and algorithms, lots of practical techniques, practical tricks, as well as software automatic differentiation platforms, right? But then the neural architecture optimization is a dramatically different area. So first of all, when people think about architecture optimization, it's often viewed as a discrete optimization, and it has a huge combinatorial search space, and evaluation cost is very expensive, right? And this field is actually very different from parameter learning. Architecture learning is, there's lots of different algorithms for architecture learning, and there's no single algorithm that can dominate yet. And many of the algorithms use black box optimization, reinforced learning, evolution algorithm, or continuous relaxation, which cannot leverage the kind of intrinsic gradient information of the objective loss, right? And these methods often rely on computational power or relies on a really smart and hand design of model space on which even random search can work well. So essentially all the successes we have now are on the model space, like design a model space rather than on a better and efficient optimization algorithm, right? So now this comes to my open questions. The really fundamental question that I want to ask, which I think there's no definite answer, is that can we have a similar killer algorithm, a unified algorithm for architecture learning, right? Would that kind of algorithm ever exist, right? In one scenario, it could be that architecture is a much more difficult problem, so we actually need different algorithms for different settings, right? Another more better setting is that we can hope one single algorithm can actually solve all the architecture learning problems, just like gradient descent can solve the parameter optimization, right? Now, another question is, if there exists a killer algorithm for architecture learning, would that algorithm be unified with the parameter learning? Shouldn't we have a single killer algorithm for both architecture and parameter learning, because they are doing the same thing, which is learning the model, except that one is training the structure, another training the parameter? Shouldn't they be unified, right? And then the question is, would that killer algorithm already exist, right? For example, the algorithm that we already have is based on reinforcement learning, that's and many other algorithms. Would this algorithm be already sufficient if we engineer them and improve them in certain way? Or do we need some brand new concepts or principles to develop some really new algorithms that we haven't seen yet, right? So how can we copy the success of gradient-based parameter learning? Can we derive, from the perspective unifying parameter and the architecture, can we actually extend the success of gradient descent to architecture learning, right? And then a final question is there a room for theoretical thinking, right? We all know that now these days, much of the new algorithms in deep learning has been invented from empirical insights rather than theoretical understandings. Would this actually change in the field of architecture learning? Okay, now I give I want to here give some of my perspective, which is based on some of my recent research. So it turns out we discovered that that's actually a chance to unify parameter learning and architecture learning. And the idea is that if we consider this parameter and architecture jointly, then we actually get a continuous optimization instead of discrete optimization. And then we can actually define, generalize the notions of gradient in this joint space of parameter and architecture and design unified and generalized gradient descent procedures for architecture optimization. And that actually allows us to potentially leverage the vast literature in optimization theory and algorithm to help architecture learning. Eventually, I hope that this can, this direction can actually combine insights from both theoretical insights as well as empirical observations to develop new algorithms, right? So now I go very briefly about the idea that I sort of mentioned. I sort of many want to convince you why this architecture learning should be a continuous problem. So the idea here is that we are thinking about the optimization in the space here, omega, of all the possible neural networks, including parameter and structures, right? Thinking about this fully connected network, then you will include network of all sizes and all parameters, right? Then, the observation is very simple. If you think about this whole space, then any two neural networks, even though they have different architectures, they can be connected with a continuous path, meaning that you can take one neural network and apply a continuous deformation to another. For example, if you have a small network, you can deform it into a larger network by adding some dummy zero neurons to match the structure and then continuously change the parameters, right? Obviously, you can do something else, but the idea is to show that this space is indeed actually a continuous space. And then what that means is that this continuous space, even though it's a little bit more complicated than the typical Euclidean space, you can define notions of gradient, generalize the versions of gradient descent that allows it to solve the problem. Right? So now the way to do that is you can you can generalize what we are doing for Euclidean optimization, define this steepest descent procedure, where iteratively you are finding the best possible solution within your neighborhood, epsilon neighborhood of your current solution. Here, the neighborhood has to be defined with respect to some distance. If the distance is a Euclidean distance, then you will reduce to a typical parametric optimization. But now if you define more general distance on the whole overall space, overall architectural parameter space, you will get a joint algorithm for joint parametric and architectural learning. And what's interesting is that even though this overall space is infinite dimensional, we can still derive practical algorithm out of this framework. So the algorithms derived under this framework will generally generally alternate between two types of phases. One is parametric descent. This is when the next point, ft plus 1, has the same structure as ft. So this will reduce to a typical parametric update. Another space is when the architecture descent, which means that the next state is going to have different architecture. This will be a new type of update introduced for parametric updates. So the algorithm will basically continue some phase of parametric descent as usual, and then you will decide to change the architecture, and then you will continue. So we have designed two examples of this, two examples of algorithms under this framework. The first work was in last year, where we designed, we take the metric over that model space to be a Walsh-Stan space. And then that actually allows us to derive something we call splitting architectural descent, where the update of the structure is performed by splitting neurons inside the existing neural network in certain optimal way. And that optimal procedure is actually solved by an eigenvalue problem. More recently, we have another extension we call Firefly architecture descent. So the idea now is that instead of defining the metric, we can directly define the neighborhood space in which we want to search for the best solution that allow us to generalize the algorithm very significantly. And we found it works quite efficiently in lots of challenging problems, and as well as challenging settings such as lifelong learning. I think this concludes my talk. To summarize, the idea is that we can potentially view the architectural learning as a continuous problem. Hopefully, this will bring advantages and bring us closer to develop a final unified algorithm for joint architectural parameter learning. Thank you.
Great. Thanks, Jian. Very interesting ideas. So up next, we have Tesh Schmidt from the Lawrence Berkeley National Laboratory.
Well, Ben, thank you for the introduction earlier, and thank you for having me. So as Ben mentioned, I am a physicist, and so I hope to present a bit of a physicist perspective on how we can ask better scientific questions with the aid of neural networks. So in this talk, I want to just briefly argue that we need principled neural networks to ask scientific questions. So often asking a good scientific question can take as much time as trying to actually answer it. So asking is a very important part of the scientific process. And so we need tools or models that make it easier for us to articulate those scientific questions. And I think neural networks are sort of a perfect means for doing this. But to do this, I want to dig more into how do we learn from scientific models? And it's often by testing what does and doesn't work. The very famous statement from George Box and others is, all models are wrong, but some are useful. And I think I even want to maybe hone that a little bit down even more. We especially learn useful things from models when they're at the boundary of working and not working. And so being able to develop network architectures that have good knobs, kind of spectrums of operations that we can turn on and off and sort of run experiments on will be immensely useful for understanding the complexities of the data we have at hand in the physical sciences and biological sciences. So what makes a scientific model good? Not only does it do what we expect, not only does it fit our data, but it surprises us by implying something that we didn't expect. And I'll give an example of this, or two different examples of this. And then what makes a scientific model understandable? Interpretability is a huge topic to discuss about neural networks, but it's just as important in scientific modeling. And there's a very famous quote from Einstein saying, everything should be made as simple as possible, but no simpler. So speaking of Einstein, I wanted to maybe give a very relevant example, especially since it was recently announced. The Physics Nobel Prizes for 2020 is about general relativity. So general relativity is just a really good example of a good model. So general relativity was developed in 1915 by Einstein to relate space, time, and gravity. And one of the phenomenal unexpected consequence of this theory was the prediction of something called a black hole, which is a massive object that exists at a point in space that curves the space around it such that not even light can escape. If you look at the equation, the Einstein field equations for general relativity, it's a deceptively simple equation. It's preposterously difficult to solve. But on one hand of the equation, you have the geometry of space-time. And on the other hand, you have where is matter. So it's the relationship of how matter and energy curve space-time. Now, I want to point out that basically Schwarzschild found a solution in sort of these Einstein field equations that suggested that black holes, these singularities, where basically space-time is so curved up on itself that light can't escape. Suggests this was in the first month of general relativity sort of being publicly available to the scientific community. So it was kind of a very unexpected but very quickly found consequence of general relativity. But it wasn't until 100 years later that we can confidently say that not only do we theoretically understand the formation of black holes, but we can also experimentally measure and verify that these objects exist. So Stephen Hawking and Roger Penrose were fundamental in sort of establishing the theoretical robustness of this. And then Reinhard Genzel and Andrea Ghez were leading the teams that found the experimental evidence for the supermassive black hole that's in the center of our galaxy. So wanted to give this very timely and relevant example of a good scientific model. Okay, but now I'm going to give a slightly smaller example that involves neural networks from my research. So I build networks that understand when different ways of representing something mean the same thing. And these are kind of fall under the general umbrella of symmetry equivariant neural networks, which Max Welling talked extensively about. So Euclidean symmetry is the symmetry of 3D space, aka where most physics happens if you're not going too fast and need to invoke relativity. And the symmetry of 3D space means that we have the freedom to choose our coordinate system. Coordinate systems are a choice. You can describe the same system with different coordinate systems, different choices of where your origin and X, Y, Z are, but it means the same thing. And so to build a neural network that understands coordinate transformations, that means that the network operations have to commute with changes of coordinate system or elements of Euclidean symmetry. So 3D translation, 3D rotation, 3D inversion, and mirrors. So I can either apply my change of coordinates to my inputs, or I can apply the change of coordinates to my outputs, and this shouldn't matter. Kind of the big picture idea is that symmetry is traditionally problematic for machine learning. If I write something down in terms of 3D coordinates, those coordinates are sensitive to my choice of coordinate system, and a general traditional machine learning method is going to be tripped up by that. It's not going to necessarily know that maybe I'm representing a benzene molecule in one coordinate system or another, but equivariant networks don't have this problem. So I want to present kind of something that we found with these equivariant networks that surprised us. Kind of to answer the question, can neural networks give us answers we didn't expect? So we asked these types of Euclidean symmetry preserving neural networks to do a simple task, two different simple tasks. We gave it 4 points in the shape of a rectangle, and we asked it to learn to displace those points to form a square, a specific square. So specific rectangle, specific square. And then we asked it to do the reverse. We asked it to take a square and then to tell us how to displace those points to form a specific rectangle. Sounds very similar, it's just the reverse task. And what we found is that with these symmetry preserving networks, it could do one task and not the other. And when we first tried this, we're a little bit surprised. We're like, hold on, what's going on? But if you actually look at the outputs, and I'll explain these a little bit more, by looking at the outputs, we could actually see what was going on. So rather than the network articulating these displacements as a vector, which vectors can only point in one direction, we actually asked the network to articulate these directions as these blobs. These blobs happen to be linear combinations of spherical harmonics, but we can think of them as blobs. So we can see on the left that the network that was able to train successfully, has one blob emanating from each blue point overlapping with one of the orange points on the square. So it's able to do the task. That's what we want. If we look at the right, we see that every point has two blobs. And what this told us is that the network is actually predicting degenerate outcomes. It's saying there isn't just one solution to this problem, there's two solutions. We only showed it one solution, but it actually understands that there's two of them. So not only can you turn the square into the rectangle that's kind of aligned along the y-axis, you can also do it for a rectangle aligned along the x-axis. And so this was really neat. We're like, wow, this actually makes sense from symmetry. Like a square is highly symmetric, and if you want to distort it into this rectangle, there's two different options. And it turns out that this is actually a very well understood, very deep principle of physical systems. And it led us to realize, wow, by building the assumptions, our assumptions about 3D space in this case, into the functional form of neural networks, we can actually fully explore the consequences of those assumptions. We started by just wanting to be able to articulate things in arbitrary coordinate systems. And what we found was what's called Curie's principle, named after Pierre Curie, or Marie Curie's husband, which is a very old principle. He first articulated it in 1894. And it's this: when effects show certain asymmetry, so the physical system has certain asymmetry, this asymmetry must be found in the causes that gave rise to them. So asymmetry can't come out of nowhere, it has to come from somewhere. And to demonstrate this a little bit more concretely, let's say I randomly initialize a Euclidean neural network with some sort, and I give it an input geometry of either this tetrahedron, so I give it these coordinates, these 3D coordinates, and I give it an octahedron, and I ask it to produce a linear combination of spherical harmonics up to a given order, so more blobs. If I randomly initialize the model, what I'll see in these randomized outputs is that they have the same symmetry as the input. These objects are beautiful and complex, but they all have tetrahedral symmetry. And these also equally complex have octahedral symmetry. And so what this brings me to say that architecture design is a key tool for crafting function spaces and being able to say concrete things about the models that are fitting our data. We can draw inspiration from existing techniques, such as scientific computing, to build principled networks. And the reason why I bring in scientific computing is that, especially for the physical sciences, we know a lot about the general functional form of physical mechanisms, and we should readily leverage this knowledge in architecture design. And also, we often know how to actually evaluate the general solution to a lot of physical systems, but doing so is computationally infeasible. So solving quantum mechanics, the Schrödinger equation is deceptively simple when you write it down, but you can use all the supercomputers in the world for, forever, and you still won't be able to articulate certain complexities. Maybe quantum computing will change that. So I think pairing context-driven solutions with traditional approaches is going to be really critical for leveraging neural networks to make scientific insights. Furthermore, we need to be able to explore what's the minimal complexity necessary to emulate a physical system, and we can do this by testing the expressivity of different neural networks. So quick recap, useful scientific models are principled, tunable, understandable, and by crafting the operations of our neural network architectures to prioritize these properties, we can build better frameworks for posing and articulating scientific questions. To give a small example, we built Euclidean neural networks to understand coordinate system changes, and we recovered Curie's principle, which is a very important principle in the physical sciences. So I'll stop there. Feel free to reach out to me if you have any questions. If you're interested in specifically Euclidean neural networks, go ahead and go to e3nn.org. We have tons of resources there, including the ones below.
Great, thanks, Tess. It's definitely an interesting perspective that a lot of us don't get to see very often. All right. And so up next, we will have Chong Yu, who's a postdoctoral scholar at the University of California, Berkeley.
Okay, so thanks, Ben, for the introduction. So I'm going to be speaking about our perspective for principal design of neural network architectures, right, from the perspective of isometric learning. So the argument here is that neural network architectures that we're using as of today are mostly a product of many years of trial and error development. And in particular, people are now familiar with this kind of standardized building blocks, such as nonlinearity, like with ReLU, or convolution and residual blocks. But actually, for each one of them, there has been a ton of work regarding what is the best way to design each one of them, right? So what I'm going to do is to perhaps do a little bit of a review of the development and see if there's any like trend or anything that we can learn from this history, right? So let's start from nonlinearities. So the nonlinearity that kicked off the deep learning error is this kind of ReLU nonlinearity, where it's an identity function for positive entries, while it's zeroing everything out for the negative entries. And upon that, there has been some early works on like leaky ReLU or programmable ReLU that was a bit of a modification on the original ReLU. So the argument that or the motivation for designing these components are really that they say, in ReLU you have dead neurons, like the entries that point to the negative half of the, the negative entries are not going to be activating the neuron. And there is no gradient, so you cannot train. So in order to address that, they are adopting this kind of slope in the negative part. And then there is later work on exponential linear unit, or like scaled exponential linear units that is more or less similar to the leaky ReLU, but they cannot provide another justification for that, right? Which is basically to say that, if you do the ReLU, then the signal is shifted towards positivity, right? Because you are zeroing out all the negative part. And they are designing this kind of more smooth nonlinear function so that, hopefully to address the issue of with ReLU. And then as people gain more and more computational resources, like people started with trying architecture search, right? Search for the best activation function in terms of, performance. And this is basically what they get, or what they find is the most effective. And even more recently, there has also been this work on shifted ReLU, or they also have other names, which is basically designed by shifting the regular ReLU towards bottom left direction, right? So, and then the motivation here is again, like they give motivation that this is used to alleviate the bias shifting effect, which is basically similar to what is being argued for the exponential linear unit here. So by and large, I think the message that I want to convey here is that for all those developments, people come up with different motivations and then they design it differently. But the question for us is really that is there possibly a unifying principle that can explain the story, right? To tell us the story that why these things should be designed like this, right? And what I'm trying to argue here is that there is really this notion of isometry that is perhaps as we conjectured as a central principle for designing these units, right? The ReLU is cutting off half of the energy, which is not an isometry, but as we move forward to the right, then the nonlinearity functions are really moving towards the isometry. So let me give you more evidences, right, from the perspective of weight initialization or weight regularization. So in here, the initial story is that people tried this kind of Gaussian initialization with the principle of variance preserving, right, in the sense that the layer should be initialized so that the variance of the signal maintains at a constant level through multiple layers. And some early works follow that principle to design a initialization for like some early activation functions. And then as ReLU becomes more popular, then there is also this ReLU activation like timing initialization. And for more general activation function, it's going to be more complicated, that you need to work in the regime of like infinite wide neural network, but still you can able to derive that. So that's the first group of methods. And then there is a second group that is based on the principle of orthogonality or distance preserving, right? Which is actually a more like restrictive requirement than the variance preserving, in the sense that if you have orthogonality, then it naturally is doing the variance preserving. So, but it's like imposing extra. And in there has also been both theoretical and empirical works to show the effectiveness of the method. And then the next trend is that people are saying that enforcing orthogonality at initial points may not be good enough. We also want orthogonality throughout the training process. And then people develop this all kind of regularization techniques for enforcing this kind of orthogonality for constants, for like recurrent neural networks and for GANs as well. So again, so if I am to summarize what is being done here, or what is going on through all these years of development, is precisely that there is a notion of isometry that is going through, right? Like people are introducing more and more notion of isometry in this kind of weight design. And then the final part is this residual learning, right? So which is one of the like most cited work in deep learning. And this is the original residual learning block. But over the years, there has also been a lot of development on the residual block. And in particular, many of them are based on putting a scalar multiplier here on the residual branch. So the original residual block can be considered as having a scalar equals to 1. But later, people find empirically, right, you can use a smaller scalar, right? So these are the initial value of the scalar, right? If you initialize the scalar to be 0 or 0.1, then they find that it's giving you a better performance. And then later, there has also been a sequence of work on showing more principled way of like setting this scalar, right? It should be adaptive to the number of layers in your network. So here, what we are seeing is again a similar trend, right, towards being an isometric transformation, because if the residual branch is small enough, then you only have the shortcuts, and then it becomes an isometry. So really, the isometry can explain or provide an explanation for why people choose these kind of scalars. Okay, so by and large, a very consistent trend that we're seeing here in all those three components is really that perhaps the notion of isometry or non-energy preserving is serving as a central principle for building neural network architectures. And this motivates us to ask a question, right? Does isometry really matters for architecture design, right? And to basically test that idea, in one of our works, we did some experiments, right? So we designed a vanilla network, where there is no batch normalization and there is no shortcut connections, so just convolution and nonlinearity. So what we did was that we want to design those two components so that they are close to being isometric, right? For convolution, we use a identity initialization, and during training, we use a orthogonal regularization to enforce that we close in isometry. And for nonlinearity, we use a shifty version of ReLU function, which is also like more closer to a isometry than the original ReLU. And then what we observed is that with such a vanilla network, right, where there is no batch norm, there's no shortcuts, we're able to obtain a fairly good performance on the ImageNet datasets for very deep neural networks, right? And here is kind of the story is that if we look at the vanilla network, then you can train for 18 or 34 layers, but not more, right? And if you add only shortcut or only batch norm, then it helps you to improve a little bit, but still you cannot train very deep neural network. But for our case, we really observed that, with this kind of isometric design, you can go with very deep network, or at least 100-layer deep networks, and still maintain a very high test accuracy. And this is, to our knowledge, the first time that we are able to train a vanilla deep network on the ImageNet or this kind of practical data sets. So I hope this provides some justification that isometry is perhaps one of the key principle or building principle for neural network architecture design. And on that aspect, there could be a lot of open problems, right? So in particular, theoretical problems, like from an optimization perspective, how does isometry helps to improve the optimization landscape? And there has been prior theoretical work on that for providing justification for isometry in linear networks, but how about nonlinear networks? And then there's also work on studying generalization of this kind of isometric or orthogonal regularized neural networks, or how do we expand upon that to develop a solid theory for that. And then there's actually even more empirical result on showing the benefit of isometry, right? And there's been a very early work on showing that it helps to improve adversarial robustness, but there is no explanation as to why or how it helps. And similarly for GANs, right? There's also been work on showing that the performance of GANs are predicted by generator conditioning. So again, there's no theory. So can we have any theory for that, right? So that finishes my part. Thank you.
Great, thanks, Chung. And so up next, we'll have Anima Anand Kumar from Caltech and NVIDIA.
Yeah, so lots of great talks so far, and what I'll talk about today, kind of echoes with a number of those principles, right? So broadly, I said principle design, but really what I want to focus is on the role of priors, because learning is really a combination of data and priors, and architecture design should be more driven by priors than what it is today. For instance, if we are designing architectures for control systems such as landing drones, we want those networks to be stable and satisfying safety requirements. For instance, spectral regularization there will help us give safe stability guarantees, and those were very effective in our experiments on adding existing controllers with learning and requiring stability requirements. In many other cases, we've used all kinds of other priors to better design neural network architectures. Tess mentioned Schrodinger equations, right? The ability to compute quantum energies is very expensive today to do it at high fidelity. They use density functional theory or DFT. But what we did was be able to replace that with neural networks, get 1,000-fold speed up, but still have transferability and have high fidelity calculations. And the way we did that was to make strong use of priors. We used molecular orbitals, which are cheaper features to compute using traditional methods. And then on top of it, we built graph neural networks in that application. So these are examples of where thinking about the domain, thinking about the constraints in the domain and the knowledge that's available. In the control, we used existing controllers and then augmented neural networks with it rather than design from scratch, right? So I think this we'll see more and more of it in the coming years, because if you ask for robustness, you cannot just use any universal approximator, right? The more inductive bias you build in, the better it'll be, the more robust it will be, the more generalizable it will be. So that's the broad principle. Today, I'll give you a few examples of such design. The one I want to talk about is with tensors, as Ben mentioned. I've been working on tensors for a number of years, how to extend spectral methods to having tensor computations for learning latent variable models is where I started with. And now these days we've been building tensor operations into different neural network architecture, right? So ultimately, if you think about any neural network architecture that's a tensor map, so there's no need to limit ourselves to just matrix computations in the layers. And what Tensorly enables us to do is have many ready-made tensorized layers, but also be able to create your own layers using simple Python code and connect to numerous different backends. So I encourage you to check it out. There's lots of example notebooks and code available on the website. And so as an example, for instance, if we want to do 3D convolution and that's very expensive, can we express that as sum of separable convolution? So you can think of that as a CP decomposition. And in the paper that I know Jean Kosefi wrote, what he showed was you can get a model that is much smaller than the state of the art, but do even better in the scores. In this case, it was tracking different emotions in these videos. So the idea of bigger is better is not going to be true if you build the right inductive bias. In fact, a smaller model can give you better generalization. And we see the same also with spatiotemporal data, where in order to do early activity detection or long-range forecasting, the LSTM is only having short-term memory, right? Like it's just not able to keep up for a longer time scale. And transformers are too expensive for videos and just not tenable, in the current scale. So given that these tensor trained models, what they do is they take a window of hidden states. So it's a higher order Markov model, but it's able to then do a tensor trained decomposition. So it's learning a low rank representation end to end. And by learning that directly, it's able to come up with compact models, so much smaller models than the baseline. Even it's smaller than the baseline, which is interesting, but be able to do better in terms of video prediction quality, in terms of early activity detection. So you can see this is able to detect the activity much early on compared to the other models. So the main principle here is that you don't have to have big models to get state-of-the-art performance. By nicely designing the architecture using tensors, you can create the relevant bottlenecks, make the model compact, learn better, and also have speed ups and lower memory requirements. So that was one example of a principled approach for architecture design. A second one I want to talk about is deriving inspiration from our own biological mechanisms, right? Like how is the brain able to have such robustness and generalization? And this is where working with Doris Saw at Caltech, who's a neuroscientist, has given me lots of great ideas and inspiration. And so the main principle is in the brain now, there is a notion of self-consistency that's happening. There's an internal generative model, representation of the world around us that we have. And so even if you have a blurry cat as the external input, it'll use the internal model to effectively denoise and detect that it's a cat in the image, right? So unlike a standard feed-forward architecture in the brain, what we have is also the feedback from the generative model in order to be able to get this robustness. And so you can think of this self-consistency in terms of effectively a cyclic condition here, right? Because you can think of it as between the input and the label, and also some hidden variables. There's lots of hidden variations that are not labeled, whether it's lighting, size, so on. So all these are aspects that you can incorporate in terms of latent variable Z. And what the self-consistency says is the most likely answer of one of the variables given the others should be consistent with the other cases, right? So if I believe there is a cat in the image, I should effectively be able to generate the features that look like a cat. So I should have this effectively invertibility, but the standard models are not invertible. And so what we'll do is introduce hidden variables, the Z, as a way to overcome this non-invertibility. So effectively we'll have this feed forward loop and a feedback loop in a generative model, and putting that together along with inferring the latent variables will give us this new network architecture. And so the way it gets built into any neural network, you can take any standard feed-forward network, ResNet, or any other network, right? So here, just simply to show it in the feed-forward layers, you can have the standard layers, such as the ReLU and pooling, but this time it becomes adaptive. So after the first round of this feed-forward, the ReLU and max pooling will adapt based on the feedback you get. So the feedback will have this latent variables as well as the G, which is the feedback signal. And your feed forward outputs are now changing based on the feedback. And this can go in cycles. And so for instance, now the ReLU, you will change based on what the feedback signal is, right? So you're changing the gating of the feed forward step based on the feedback input. And so this is the top-down inference that is now being able to iteratively change the answers of the feed-forward network. And what we see is even noise that is never seen during training, it can correct it at test time. I mean, this would be impossible for a standard feed-forward network. But because now we've built also a generative model for feedback, so we've trained it with a generative loss to reconstruct intermediate features, and they reuse the same weights as the feed forward network. We have effectively a Bayesian model that can do both generation and prediction. And so any noisy image, it can now try to project to the clean manifold, and hence it is able to repair all kinds of distorted images, so all kinds of different noise. It's never seen during training. At test time, it can iteratively refine this. On MNIST, we can visualize this, but for larger data sets, for larger images, we would be reconstructing only some intermediate features and not in the pixel space. And that's what we've done in a number of settings. So this is Fashion MNIST. We also have CFAR in the latest results. But the main takeaway is it has inherent robustness now because of feedback. This is standard training. So the standard feed-forward network has very little robustness, right? Even with a small amount of noise, because it's never seen it during training, it just significantly degrades very quickly. Whereas you can see that this holds up to a much larger range of noise. So it's able to have this inherent robustness because of this feedback architecture. Yeah, so I think this kind of design where we take inspiration from the brain and bring that into our neural network architecture design can give us a lot of nice properties. We explored robustness, but the ability to do online learning, the ability to do good uncertainty quantification, these are all aspects we hope to establish in future. I think these kind of models that are hybrid are essential for that. And ultimately, Bayesian inference is expensive, but the way we do the architectures to make that efficient and have as little approximations as possible, I think we'll get better results in all these aspects. Thank you.
Great. Thanks, Anima. Someone who did a lot of systems neuroscience in a past life. I always like biological inspiration. So. All right. So up next, we will have Song Han from MIT.
Yeah. Okay, great. All right. So just now, Nima talked about this important concept. Smaller networks compared with the larger networks, not necessarily is bad, right? And in many scenarios, we are tightly constrained by the computation resources. For example, can we deploy deep neural nets on tiny microcontrollers, which has only 1 megabyte of flash and only several hundreds of kilobytes of SRAM. So how can we scale down deep neural networks to such resource-constrained IoT devices, but still achieve ImageNet level inference quality? So I'm going to introduce our recent work on MCUNet tiny deep learning on IoT devices. So AIoT is basically AI plus IoT. The concept is getting very popular recently to deploy neural networks on those low power, low cost, always on microcontrollers, which has a rapid growth in recent years, which has a wide range of applications such as smart retail, personalized healthcare, agriculture, and smart home, which we want to deploy those sensors and microcontrollers on edge devices. So from cloud AI to mobile AI to tiny AI, we are having tighter and tighter memory constraints. GPU has like 16 gigabytes of memory. A mobile phone can have like 4 gigabytes of memory. Well, tiny AI scenario, we have only hundreds of kilobytes of memory. So how can we design neural nets that can fit these 4 orders of magnitude smaller memory constraint? Conventional neural architecture design focus on reducing the number of parameters. However, the activation is the main bottleneck for the inference SRAM. Like MobileNet has smaller number of parameters, but the activation is not optimized. So we want to rethink how do we design the neural network architectures for the tiny AI setup. So this is a comparison between Resident 50, MobileNet v2, and MobileNet v2 quantized version. So Resident 50 require peak memory 23 times larger than the memory constraint of a microcontroller, which is only 320 kilobytes or even less. MobileNet v2, although the number of parameters are less, but the peak memory consumption isn't much less compared with Resident 50. It is still 22 times larger because of the wrong design target. We need to optimize the memory, not just the number of parameters. Even the quantized MobileNet v2, 4 times smaller, is still 5 times larger than the memory constraint. And as a result, conventionally on microcontrollers, we can only do those simple tasks under very low resolution, like classifying oranges and pears and apples, etc. And how can we push to full ImageNet, 1,000-class ImageNet classification under such tight memory constraint? So how do we save the memory during inference? So MCUNet have 2 components. We co-design the neural network architecture with the compiler and the runtime. So conventional neural architecture search approach assume a fixed inference library, say TensorFlow Lite, and only design the neural network architecture. And conventional compilers and frameworks such as CMSIS-NN from ARM or the TVM assume we are given a pre-trained model and we design the inference library to speed it up. So our work, we co-design the neural architecture with the inference library, including the compiler and the runtime. So we jointly design the inference engine with the neural architecture. Okay, so there is no operating system, therefore we need to carefully manage the memory for the weights and also the activations. So the design principle for our co-design is that there is no pre-designed design space for neural architecture search on tiny microcontrollers. There is plenty of work of neural architecture search targeting mobile devices like mobile phones. However, very little work has focused on how to design the design space for microcontrollers. Therefore, we propose a method that can narrow the design space to fit tiny microcontrollers by plotting a curve with the flops as the y-axis and as the x-axis, and the y-axis is the proportion of the models given such design space fitting the memory constraint. What is the maximum amount of flops that can be achieved? Assuming that more flops means higher model capacity. Using this method, we select the best performing design space. And then we use the once for all network that train a super network that is composed of a larger network than we actually need. And then we select a subnetwork. So we first train a over-parameterized network and then select a subnetwork. And we find this method works pretty well designing and searching small and compact neural network architectures. And for the tiny engine part, so that part is the tiny NAS part. For the tiny engine part, we adopted several techniques to save the memory at the runtime, including offloading the interpretation-based framework into compilation-based. So we move lots of the runtime overhead to compile time. And secondly, we applied the in-place depth-wise layer, which consumes half of the memory footprint, since we can compute the input feature map and also the output feature map completely in place. So by combining these efforts together, we can shrink the peak memory by 3.4 times compared with ARM CMC's NN by using the code generation and in-place depth-wise layer. Okay, and by combining our compilation and runtime optimizations with code generation, we can speed up the throughput speed from 52 million ops per second to 64. And then applying specialized image to column, operation fusion, loop unrolling, and tiling, we can altogether achieve 1 point times faster. This is faster inference speed compared with the ARM CMC's NN. So compared with the baseline, which is MobileNet running on ARM CMC, Google's MobileNet v2 running on ARM's CMC's NN, which achieve only 39.7% top-line accuracy. Our method, if we replace CMC's NN with our tiny engine, we can boost the accuracy to 43%, given such a tight memory constraint, 320 kilobytes of SRAM, 1 megabyte of flash. And if we replace Google's MobileNet v2 with our tiny NAS, we can boost the accuracy to 55% top-line accuracy. But if we apply co-design with our tiny NAS plus the tiny engine with the same constraint, we can boost the accuracy to 61.8% top-line accuracy on the full ImageNet. We are pretty surprised with the result. Back in 2012, when AlexNet just came, the accuracy is roughly 57%, but that is requiring a GPU. Now we can do everything just run on such a tiny 1 megabyte of flash microcontroller. We also compared with diverse hardware platforms from a 256 kilobytes of SRAM, 1 megabyte of flash, all the way to 5 kilobyte of SRAM to 2 megabyte of flash. We can achieve an ImageNet accuracy all the way up to 70% top-line accuracy, which is the first to achieve more than 70% ImageNet accuracy on a tiny commercial microcontroller. And finally, we have a short demo showing that we can run this at a higher frames per second compared with the MobileNet plus TF Lite, detecting person versus no person for several IIoT applications. Okay, so in summary, we proposed the tiny NAS and tiny engine, co-designing the efficient neural network model with the compiler and the runtime for efficient scheduling and fitting the tight memory constraint. And our studies suggest that the era of tiny machine learning on IoT devices has arrived. And the okay, that's all for my presentation. Thank you.
Great. Thanks, Sung, and thanks also to the rest of the panelists. Great talks all around. So now this sort of opens up the more discussion panel part of the session. And so first, I'll just ask if anyone has any questions they'd like to ask any of the panelists. And if not, I'd actually lead off with one of mine. And so really, you know, if you think about sort of principled neural network design and theory and these sort of things, you know, what I sort of view as the holy grail is really kind of you know, some modular theory of neural networks, right? So can you say something about small pieces of the network, and then really how will they interact when you connect them into larger, more compositional sort of structures, right? And so this can be done at sort of a lot of different levels of abstraction, you know, all the way down to single hidden units to more, you know, convolutional filters, even, you know, in sub-network architectures. And so I was just curious if, you know, if some of the panelists could maybe speak about how some of the topics that they talked about could sort of inform those sort of things. So for example, you know, maybe modules that are equivariant or respect certain physical principles or incorporate certain, you know, Bayesian priors, computational constraints, etc. Could all sort of be potential considerations that would go into, you know, a theory like that. So I don't know if any one of the panelists wants to jump in first, or if I should call on somebody. But
well, I can you know, take a stab at it.
great.
I think, you know, this goes back to the principle of asking what from the domain is a constraint to enforce, right? Like, for instance, in the case of control, having stability, safety requirements, those are, you know, constraints. And the question is, can we build that into the architecture rather than have it just be purely data driven? So I think a lot of that could come from the domain. And then, you know, I think the aspect of like how to build it into modules, you know, is kind of then going towards neurosymbolic AI, right? The question is, how much of symbol grounding do we do at which level of abstraction? And especially if there is no supervision, then it's hard to do it. But in cases like program code, where we have all the supervision, how do we build the right level of abstraction? You know, which part should be neural, which part should be symbolic, and how do you check that it's learning good intermediate representations as well? I think we should first look towards domains like program code with all the supervision available, and you can do any level of compositionality, right? Like there is you know, all kinds of different combinations of math functions we can do, whereas in the real world images only certain combinations occur, so you cannot systematically test for compositionality. And speaking of benchmarks, I think that's also important. Like, we have to think about not just designing architectures that are compositional or modular, but how do we systematically test for that? And that's where, again, you know, having it in the math domain becomes easier because you can generate equations, you can, you know, do this differential equations or integration, theorem proving, all these aspects. And you can ask about systematic generalization there, to harder examples, to out of distribution. And if you look at those cases, the current transformers, while they do very well on the same distribution, they, you know, very quickly degrade as you even slightly change the distribution, right? So that means, that shows that they are not able to do very good compositional learning. They are overfitting to the distribution. And lastly, I want to you know, talk about a paper that's coming up at NeurIPS, where we have a new challenge called the Bongar challenge that is having the ability to now carefully test for compositionality and generalization for visual reasoning. These are fairly simple visual shapes, right? But the difference is, it's still an infinite vocabulary. We use the logo program to generate all kinds of variations. And every example, it's few shot. Every problem instance is just 6 positive and negative examples. So, you know, but we have tens of thousands of such problem instances. So the idea is, can it learn different concepts by seeing variety of such puzzles? And it's not just pattern matching, because the same concept can be, the same figure rather can be having entirely different concepts in different problem instances, right? Because each figure can be described in many ways and has different conceptual properties. And so that's a challenge where, you know, it looks very simple shapes. Humans have really high accuracy, you know, sometimes as high as 99%, if they are carefully doing these puzzles. But even the best meta learning methods have, you know, somewhere in the higher 60s when it comes to accuracy. So there is quite a big gap of what humans can do and what machines cannot do, even on fairly simple shapes, right? We don't have to go to very complex real world shapes to test for compositionality and reasoning. But then we found like neurosymbolic methods there have the best performance compared to all the other methods. So it shows the power of having the symbolic grounding. So I think that's a challenge where with new methods need to be tested because we've barely scratched the surface there. So I'll stop.
That sounds great. We're working on another project on sort of semantic information. I think we were sort of looking for a challenge like that to test it on. So that sounds great. Would you mind posting the link to that in the chat maybe?
Oh.
And I guess maybe just kind of a follow-up question on that. If we do sort of want a compositional modular theory of neural networks, are there any thoughts on really it's not really clear to me how we want to characterize modules or networks, right? So if you think about, traditional circuits or something, you can say something about, resistances, impedances, digital logic circuits, et cetera, right? But, in terms of what the sort of key properties are of, sort of functional blocks that you're going to then connect and train together, it's not clear to me what exactly, what should a theoretician care about characterizing of those blocks to try to combine order theory? And so I don't know, that's kind of an open question, I think, for the field. I don't know if anyone has any thoughts on that, but this is something that's bothering me.
Yeah, maybe share some of my thoughts on the hardware side. So taking hardware constraints into consideration, designing hardware-aware neural networks really paved the way for us to be able to deploy and use those neural networks in practice. So a rule of thumb is computation is cheap, memory is expensive. So when we are designing neural network architectures, a good approach is to design neural nets that has high arithmetic intensity, which is defined as the computation flops divided by the memory footprint. Since access the DRAM could be 2 orders of magnitude more expensive than multiplication and add. So doing multiplication and add is literally free with respect to energy. So we should not just optimize for low flops, but we should optimize for low memory footprint.
Great.
I think that maybe chiming in on, again, the scientific application perspective. In our case, the application is really driving what types of operations are even reasonable to consider. Again, you can use very expressive general operations for scientific applications, but in a lot of senses, it can be complete overkill, or your model's actually learning something that is unphysical, or it's using information that it really shouldn't have access to, like being sensitive to coordinates, when coordinates are arbitrary constructs that we use just to put physical systems in computers. So in that case, what your modular operations become are really restricted by kind of the domain that you're applying to. So I think I'm echoing a lot of what Anima said earlier.
Yeah, great. No, I think that's definitely important. And then also, I think just kind of a follow-up question for you, I guess, as a physicist or a scientist, in the hard sciences, I guess, are there sort of aspects of machine learning that, statisticians and that sort of thing could contribute that you think would be, worthwhile for someone in the hard science or the physics?
Yeah, no, I think the help and contributions from folks in CS or stats can be invaluable. I think the biggest thing is actually just having conversations with scientists, and also not making the assumption that it's like, oh, like this problem maps to this problem, therefore use this network. Sometimes there's a lot that can be learned from both sides, I think, from having conversations about what can we tailor a method specifically for this application. So kind of being application first, not just saying, okay, well, what can we just import from things that have worked in maybe more general applications that I think for the sciences, more specific is often better.
Does anyone else have any questions? I could keep going here, but
yeah, I want to comment on the module theory question about neural networks. I think it's a very important and very interesting perspective that the neural networks, you can think as certain circuits of modules, right? Then obviously it has two questions. One is how could you decide what kind of modules are we going to use, right? What types of convolution, what types of activations functions are we going to use inside our neural network? Another part is how are we going to connect these different modules to form a circuit of deep neural networks, right? I think both questions are very interesting. So from our work on steepest descent, we have been focusing on how can we taking a set of existing modules and put them together in a kind of fastly descent version to kind of optimize the network structure. The question that how can we design modules such that it will be easier for optimization is very interesting. I saw, isometric property is a very interesting perspective, and some sort of equivalent in terms of physics property, probably some kind of neural symbolic properties can be integrated. I would be very interested to see if that's actually a overall principle that allows us to guide the design, systematic design of what kind of modules is going to be easy to learn, right? I think, and then there's another very interesting question is that besides the properties of individual modules, we can also talk about how these modules should be connected, right? I think Anima's work on feedback loops is actually a prior on which we want to put on how these modules should be connected. We should prefer this kind of feed loop in order to have the self-consistency. So that's also principles about how should we connect these modules. I think that's another very interesting question to think about.
Yeah, great. And I guess just sort of a more detailed follow-up question for you, Tiang. So in your splitting framework, is there any limitation on how general, say, a module could be, right? So you mentioned splitting single units. I think I've heard in your talks, you can split convolutional filters, let's say. But is there any limitation in terms of how that could generalize to, if you had a more complex model and then split it into two modules, let's say, and continue the optimization that way?
Well, yeah, that's a very interesting question. I think it's related to the kind of the comment I had earlier. These are two questions, right? One is what kind of modules, what kind of candidate modules are going to use in the algorithm. Another is how do you connect these modules. So my algorithm actually doesn't assume any specific knowledge about the modules. Each module really is a template of functions that is indexed by certain parameters. So you can think of each module as a parametric function. So that parametric function is defined by the user, and then algorithm would just take that parametric function. They can copy the parametric function. They can connect parametric functions in parallel or sequential way. So so that's my impression.
Yeah, and then I guess this is another detailed sort of follow-up in terms of what you can prove about it. Are there any properties on the module that let you say anything about conversions to local minima, global minima, stationary points of a given order, anything like that? That sort of go into the design of what modules might optimize well or not.
Yes, it is. Yeah, that's also a very interesting question. We can. I think it's very promising that we can prove very rigorous results under this framework. We have some recent work that actually shows that we can prove generalization, not generalization, the optimization for two-layer neural networks. So if we assume simple, let's say standard fully connected network, then we can show that under that steepest descent, you can achieve a epsilon training loss with at most certain steps of splitting descent. So this is very encouraging. I think obviously that's a more general question about what kind of, for example, can we extend this to convolutional networks, right? Convolutional neurons or other things. I think it's a very interesting open question. And I generally feel like that should be, it should be a fairly general criteria that allows to get the guarantees.
Okay, great. Does anyone else from the audience have questions, or I can keep going on some of mine? Okay. Well, then I had actually a question for for Chong, you mentioned sort of the role of isometry as a principle for design of neural networks. And, if you sort of take the, underlying low dimensional manifold model of, modern data, that a lot of the data comes from some low dimensional manifold in the ambient space, when you think about isometries, it depends on what your distance metric is, right? And so a lot of the things you were sort of talking about, it seemed like sort of isometry with respect to maybe Euclidean space, in terms of ensuring that linear operators are isometric. But have you thought at all about being isometric with respect to manifolds, or if there's any operators that could be designed so you don't necessarily know the manifold, but perhaps you could say something about whether the operator was actually isometric with respect to like a geodesic distance or anything like that?
Yeah, I think that's a very interesting perspective, right? I think I mean, I was primarily showing some evidences that, isometry is being helpful, right? But so I think we don't really have much idea. And I think there could be multiple like factors that are playing a role here, right? One of them perhaps is with respect to optimization, right? Because ultimately we are training a multi-layer structure, right? Where the signal propagates through multiple layers. And that's why perhaps like why we need isometry, so that the signal won't explode or vanish, right? So that's a classical issue. And I think the issue you mentioned was a very good one. And I think that perhaps is more related to perhaps generalization, right? In the sense that because the data do not span the entire space, so perhaps there is no need to preserve the structure or preserve the distance within the entire space. We only need to preserve the structure within the data manifold, right? And so perhaps what we really need is the notion of restricted isometry for the purpose of getting better generalization, right? Or restricted with respect to the data manifold. I think that's going to be an interesting direction to explore, but I think at this point it's not all clear to me how we should impose this kind of notion of restricted isometry.
Yeah, great. And I think that also, potentially ties in, if you have a manifold with symmetries and these sort of things, and also might sort of tie into, sort of physical constraints and stuff, sort of relating to what Tess and others were talking about. Okay, great. All right, so I think we just have a few minutes left. Are there any other questions from any other attendees?
Yeah, this is Yi. I'll just say a few words just to probably help conclude. Thanks everyone for such a great, very diverse panel, and also speak from really scientists to hardware design, to algorithms, and also to biologically inspired, and maybe some geometrically inspired design. I think this is a very touch upon everything, but this sort of reminds me sort of early days of control engineering, right? So we had a feedback system. We figured out some theory and also the foundation being laid. Now we face all the different network, the system design, right? For mechanical systems, for helping scientists. So I actually remember one of the first, the first engineer won Nobel Prize is actually a control engineer, right? Helped. What really that says is that can we really carry on from this point to design truly trustworthy systems with guaranteed performance, help scientists, right, to the level of precision and predictability. And also, like Han-Song's lab, right, really go out, all the control systems everywhere, controlling micro system, bigger system, and industrial systems, right? So with efficiency, with guaranteed safety and robustness. The same with, of course, many other application areas, right? Or helping you interacting with biologists, I think. So I think we have reached that point, right? It's kind of a charge for the community that can we build very reliable, efficient, predictable networks now, and our systems, right? Through composition, through optimization, through really mathematical design, principle design, really be able to in the field area make impact, true impact. Let's say in science, maybe next Nobel Prize winner will be, or at least one of the winning team will actually using some of the techniques, discover things that really verifiably correct, and so on. The same with biologists, right? Maybe discover some truly mechanism of what happens in brain or neuroscience and so on. Right. I think that's really is the next challenge facing everybody now, especially in this audience. Right. Can we build reliable networks and efficient and robust, and also that's also the purpose of this workshop, as well as maybe the continuing effort of this community. Yeah. Thanks.
Great. Yeah, so I guess just to conclude, thanks all of our panelists for agreeing to participate. I think it was some great ideas all around.
One thing, Ben, I was having the idea, right? So with the workshop, can we, I think the community has been diverse, very, vibrant, very active. This might be a good time. One of the thing we hope that each panel or session, we can come up with some kind of, even just not necessarily high integrated, but I mean, the things we think are really the challenge in front of us next 2 to 3 years or 5 years, or even 10 years, if there's such vision ahead. I'm just hoping that, after this, this maybe not the end of it, if you guys can have some kind of circulation of ideas or assemble some document, maybe help the young people or the other researchers in the field. And this is sort of a small charge for you with some formal documentation from this. And maybe a few years from now on, we'll look back, we maybe find that what we're discussing today actually can have a big impact in the future, right? So that's just a simple quest. Yeah, so I'll leave that to you and the rest of the folks.
Okay.
Thank you very much.
All right. Thanks, everyone.
Thanks, everyone. And also thanks for all the CDTI staff and also supporting team. All right. That very much concludes the workshop. We will probably do this on a very regular basis, if not every half a year, probably at least the one every year in the next few years. So I really hope many of you will still coming back and contribute. All right. Have all more insightful discussions. All right.